So let me just share my screen. The typical process is just to actually go through the lecture notes. Is that what we typically do? I'm sorry, I missed the last couple of weeks.
Yep.
Okay.
Yep.
Cool.
And we just discussed the interesting aspects of it. Yeah.
Okay. Okay. Cool. So first of all, well, thank you for letting me talk. But the second thing is, I haven't. My knowledge of this isn't that great, so I welcome any input in this space. I've gone through the videos, but I'm by no means an expert, so please jump in and keep me on the straight path. Hopefully everyone can see my screen. Is that okay? Do I need to make it bigger? Is this okay?
It's good.
Okay, good. Thank you. So my understanding of what we're going to go through is a couple of things. It's really about a couple of different methods of creating self-supervised learning. How do we generate features and group them from unlabeled data? So I think we're going to go through a couple of them. This is the first one, which is the discriminative recurring sparse autoencoder, which is a mouthful. For those of you who are interested, there's a paper on this from Jan LeCun. I'm not sure if there's a link to it, but if you don't have it, it's kind of interesting reading. Anyway, if you just Google it, I'm not sure where to put it on the chat, but oh, here we go. Here's the chat. There we are. Anyway, so that's it. So, but anyway, if we go through it, I'd welcome your feedback. My understanding of what we're really doing here is we're taking an input. We're taking it through an encoder. And let me kind of like read through it. It's probably better if we just follow the notes. So we take it through the encoder WE, and then through a non-linearity. Then we basically go through a bit of an encoder. I'm not clear what exactly we're doing here, but I think what we're doing is basically more of a traditional autoencoder. I mean, anybody want to jump in and just go into detail of what we're doing in this green box? I mean, I can go through here if you like, but I myself wasn't 100% clear. Okay. If there's no volunteers, I'll kind of read through it and just welcome your feedback. Okay, so my understanding is what we're doing is basically we have an encoder where we've gone through a couple of presentations earlier. Then we're taking it through a matrix, which is basically that we're going to train, send through non-linearity, and then we can repeat this pattern a number of times, I guess, depending on how complex the feature space is. The output of this is going to be three different things. The first one is going to be the reconstructed input. The second thing is going to be basically a grouping of the features is my understanding. Minimization of the number of features. So in terms of criteria, we apply a loss function to the feature vector to make it sparse, because we want to have the minimum number of feature groups possible. As I mentioned, we reconstruct the input. Not sure why we do this, but I think that has the benefit of enforcing a sparsity. I don't know if anybody wants to jump in and mention why we actually have to reconstruct the input. Okay.
I think that's the main concept of autoencoders, right? You are trying to reconstruct the input, you compress it, and then you reconstruct it from the compression. And
yeah, but
in that process, you learn good features, right?
Yeah, well, I wasn't clear. I mean, you're absolutely right. The whole concept of an autoencoder is just you reconstruct what you, but I'm not sure what benefit that has to actually clustering the features.
I think, sorry. So I think the objective here was creating the sparse features. And so, that is like a side additional objective that you give it, right? So, but you still need the main objective, which is to recreate the input, right?
Mm-hmm.
And so what it would do is kind of, as it recreates the input, because of these additional, other heads that you got, right? So the classifier head and the sparse vector head, right? Because of those, in the process of doing the autoencoding, it will also generate these two, because so you need the middle thing basically, right? So that's what I got out of it, at least. Yeah.
Okay. And can you maybe explain to me what L1 is actually doing? Your explanation of X and Y makes absolute sense, but then we have the loss function L1, and that is, it says here to make the feature vector sparse.
I'm not 100% sure, but I think it's like an L1 regularization on the various parameters, right? The coefficients. So you're basically pushing down the coefficients, and because it's an L1, it doesn't gracefully go down to zero, right? It kind of, it's steep and it's sudden, right? So coefficients which are too low would automatically get zeroized, and the remaining ones would remain as the sparse vectors, sparse features, right? So again, I mean, this is totally, I'm not an authority, right? So,
No, never mind. Sorry, someone else want to jump in?
As much as I remember from the previous lecture of Jan Lucas, so what he was saying that Z is a latent variable, if I remember correctly. Now, if you have a Z which is very strong, then what it will do, basically, it will replicate the Y directly. So what we try to do is we try to put some limitation on the variations which Z can have, so that it basically does not start copying Y and put it there.
Yep.
And so the importance of, the X won't be affecting the output in that case. So in that case, we put a some sort of the L1 is one of the regularization that we can do. What it does, basically make sure that the Z is sparse there. So it suppose so basically the sum of the total number of coefficients is limited there. So in that case, as Sujit was saying, that what it does is basically puts a regularization so that the effect of X is also expressed. It's not basically limited to Z copying Y, and then in the end we are ending up with the latent variable only affecting the final output.
yeah, I think
one thing I'm not clear is autoencoders, they're easy. In terms of optimizing them, they're straightforward. You want the input the same as the output. The cost function is pretty straightforward. Here, I see that we're optimizing at least two things, or am I mistaken? Because you're kind of looking at like L1 WD and WC, the W cost function. Am I mistaken? What are we actually optimizing? Is it just the WD, the decoder, or are we doing all three?
I think we are doing all three, and we are learning them jointly. So, typically, if you're doing, say, segmentation and classification, right, you could, combine the two things, and they actually work for each other, right, to help each other. Mm-hmm. So, I think that's what kind of is, the multi-headed outputs are usually done because of joint learning.
Okay, that makes sense. Thank you.
Yeah, sure.
Anything else before we move on to group sparsity? Okay. Well, thank you. That makes it a lot clearer to me.
So this classifier is just a normal image classification task. Is it something like that? The WC that we see here.
Yeah, that's what he claimed.
Yeah.
Okay.
I think that's an example. It doesn't have to be images. I can see this being used for NLP or something like that. I don't. I don't know why it would be limited.
So as I remember, so I think one of the reasons why we include the classification task as well as reconstruction task is that like on practice, it turned out that it's not so easy to use the features learned by autoencoder on some say classification on downstream tasks. And probably this joint learning is done with idea to enforce the features to be useful for the downstream tasks, because that is not always the case with autoencoders trained with only like plain autoencoder objective.
Yeah, that makes sense. Thank you. Anything else to add before we move to group sparsity? Okay. Thank you. So in terms of group sparsity, this is, I think, one of the examples that Jan focused on, which is basically you have the input, you go through an encoder, nonlinear, I think this is like L2 pooling, I think. Autoencoder with group sparsity here, the intent of it's going through an L1. I think my understanding is that this is basically a standard autoencoder. It basically goes through a nonlinearity, arrives at the Z function, and then it goes through a linear decoder here. And here we do L2 pooling and to arrive at the features. Now, at a high level, my understanding of this is, imagine you have an image. You're basically trying to extract features from those images. And when you extract features, what you're essentially doing is taking the input information and then doing CNN pooling, whatever, you know, like, and then you're arriving at features. And what you're doing at this stage is essentially doing something very similar, but in a linear sense, because it's all like fully connected, and trying to group those features. To me, it's like you've got the input feature space, input space. You've performed pooling, you've performed regularization, you arrive at the feature space, and then you're doing something not too dissimilar to the feature space in order to group those features. And at a high level, that's my understanding. So, I mean, before we drill down into it, would you guys disagree with my high level conceptual understanding of that? Okay, so let me kind of go into it. So here we have autoencoder, and what we're trying to do is enforce group sparsity. So here we have the latent variable, which is identified through the encoder and nonlinear transformation. You arrive at Z. Then it goes through, instead of going through L1 regularization, it goes to L2 regularization and generates grouping. Okay. So let me find a better diagram here. I'm trying to find the diagram that actually Jan had. Let me kind of go through it. Before I move to this, any comments before we can move to the next section? So do you guys want me to go through the questions and kind of like discuss them? Is that okay, or I'm just wondering what the most productive use of our time is. Should we just go through each of the questions? Okay. I'll take that as a yes. Okay. First question, can a similar strategy used in the first slide with the classify regularize be applied for the variational autoencoder? So I think from the video, he basically said, I mean, essentially, adding noise and forcing sparsity are just a way of reducing the space for the latent variable. So whether you use noise or whether you enforce sparsity, it's pretty much the same thing. What you're really trying to do is generate a lower dimensional latent variable, and you want to avoid overfitting. So you know, either noise or sparsity helps with that. Any comments on that?
Yeah, I thought of it as, you know, another kind of autoencoder. So the VAE was one kind, and you know, here is another one where you can do group sparsity, and this is how you do it. You know, that's what I took out of it. But yeah, I think you're right. Yeah.
I think what the other gentleman said is actually spot on. I agree with. I'm not sure who said it. I apologize. Basically, that is that typically an autoencoder produces features, latent variables, which are not very useful downstream. So what we're trying to do here is to generate the minimum number of features. I should say features, not variables, features that are usable. And this is one way of doing it.
Right, right.
So,
and if you look one paragraph up, right, where it says these groups, no, the caption of figure 2, actually, sorry. So the last sentence actually gives it, right, tells you this very clearly. So these groups or pools of features tend to group together features that are similar to one another. So you can actually clump them and, you know, use them as single features, right? Groups of single features.
Okay. No, thank you. Thank you. So I don't think we have the slides here, but I think what he's really talking about is in slide A with group sparsity, what is PJ? Essentially, we're trying to do pooling of the features, and in terms of like and the grouping of them. So that's what he's referring to here.
What's puzzling is the last sentence of that paragraph or, you know, explanation is directly contradicting the answer to the last question.
Okay.
Because the last question's answer says, does group regularization help with grouping similar features? And it says the answer is unclear. Whereas what you have highlighted says these groups or pools of features tend to group together features that are similar. So either it's unclear or it's clear, and that's what is happening. So I don't know which it is.
Yeah, there was a comment during the lecture. So he said, like, these are things that people used to do before, you know, like, you know, full, you know, mainstream deep learning research became a thing. So, you know, he basically mentions these as background. I don't remember the exact place though.
Yeah,
so
it may be that, you know, GradCam or other techniques to identify whether the features are in fact being grouped weren't available. So it wasn't demonstrably proven that they were, but that could have been a tentative explanation and hence the answer at the end. But I guess my concern is, therefore, it is not entirely true to believe that it does do the grouping.
Yes.
It's kind of still TBD.
Right. Yeah, he mentioned giving you weapons for future or something in there. Yeah.
Yeah, you know, I actually saw Jan LeCun present at our company a year and a half ago, and he's really into self-supervised learning. That's something that is really pushing. So I think all of this stuff is very much in his focus area, which is building the tools around self-supervised learning. But I think it's very gestational, very new. I have not seen much of these types of autoencoders out there. I'm not sure if anybody else has. I welcome your opinion. I think this is very gestational stuff, very, very cutting edge. Okay. Then let me quickly go through the next question, which is clarification on feature pooling. Encoder produces a latent variable Z, which is, or Z, sorry, which is regularized using the L2 norm of pooled features. And then this Z is used by the decoder for image reconstruction. Okay, that sounds like by definition what an autoencoder does. And then I think we're going back to regularization. Okay, I think we've gone through that. Okay. I think we've kind of like gone through this, which is yeah, this is some of the background information that he mentioned in the video, which was basically, does regularization help? So, you know, it was basically saying it's unclear. The people originally doing this, which was about 10 years ago, were doing image restoration. Obviously, image restoration has moved on quite a bit since then. It doesn't actually use this, but nevertheless. So when you have an autoencoder and encoder and a decoder, this convolution you train with group sparsity on complex cells. And after you're done pre-training the system, you get rid of the decoder and only use the encoder as a feature extractor. Okay, that's by definition what you use an autoencoder for. Okay, that makes sense. Any question on that? I think we kind of covered the regularization. If not, I'll kind of move on to the next section. I don't remember this slide from the video. Does anybody recall this? Not sure if I missed this. It kind of looks like a restatement of what we had earlier.
Yep. This slide wasn't present in the video or in the slide deck that was provided. This is a kind of new slide. So yeah, it just says the image that is going through the convolution of the REL or the scaling layers and the pooling that is being applied via the grouped features. So yeah.
How is that different to this? It looks like the feedback loop doesn't exist, but you were talking about essentially an encoder, nonlinearity, L2 regularization, and get that, but it's missing this. So if I look at this, we've got the image, we've got the convolutional layer followed by nonlinearity scaling. And then I don't think this is a decoder. I think this is just a standard CNN, and then it goes into a decoder. And L2 pooling. Yeah, I'm not sure where this is coming from. Maybe if we read it, we'll kind of go into it in detail. Anyway, you start with an image. You have an encoder. Okay, I guess this blue box is an encoder, which basically, which is the convolutional ReLU and some kind of scaling after this. Then you train it with group sparsity. Then you have a linear decoder. Okay, and this is what I was talking about to generate those toroids. Okay, and you take group sparsity as a regularizer. Okay. So this is a particular implementation that he used to generate these, in this case, it's a two-dimensional images of the feature set. And then you can add more layers and decode it with L2 spooling, etc. Okay. You can train another instance of this network. This time you can add more layers and have a decoder with L2 pooling and sparsity criterion. Train it to reconstruct its input with pooling on top. This will create a pre-trained 2-layer convolutional net. Okay. And this is the stacked autoencoder, okay, which I think you mentioned on the video. I don't have much to comment on this. This is not my forte. This is not my space. Would anybody like to add anything? I think this is just an implementation of the above and an example of, and this segues into what I think he was talking about with grouping and these visualizations. Anybody want to just comment on that? So yeah, I'm definitely not an expert on this, so I apologize. So anyway, so once you've taken an image and you've basically derived the features and you do feature grouping, then you essentially that's going to be a linear decoder. You're going to have a bunch of features, and those features can be then displayed in a 2-dimensional image. And this is like, I think you mentioned, it doesn't really matter, it could be 2, 3, whatever, but essentially this is an example of that. One of the ways of displaying it is as trees. So should we use all possible subtrees as groups? You can multiply, you can use multiple trees if you want. You can train the tree with a bigger tree that's necessary, remove branches rarely used. My understanding of when he was talking about trees, it was in the context of basically feature grouping and where you could basically treat the features and the sub features out of that as essentially a classical a tree diagram. This is my understanding correct?
Yep, kind of. In which we can also think of it as the filters of periodic kind of locally connected graphs. This is in context with the neuroscience patterns, in which we get the local receptive fields of the network. So if you think about this whole setup in the edge detector kind of an example that has been given here, we can visualize it as a kind of a latent space which is connected by multiple trees. Those pinwheel pattern, which this is called, it's kind of a feature set that's organized across those red dots that we see. So this can also be represented in a spherical tree fashion, as has been shown in the in the slides for example. I think so. There are a couple of slides too, or in the video. Yeah, that's there.
Yeah, thank you, Mayank. That makes a lot of sense. And going on to this, it's basically, I think this was one of the implementations that he mentioned of the different type of feature grouping, which I think is lateral inhibition that he mentioned. So when you have the inputs and the latent variables, these are all like cross-connected. So I think the key here that I had was the actual the L2 norm of the groups is actually I guess trained or identified. And that can be either structured or unstructured. It can be completely learned, or there can be some rules enforced in that. And this is another way of actually creating groupings of features. The outcome of this is my understanding. Again, Mayank, I welcome your feedback. Is that the way that it's trained, having one feature forces the other features or feature groups to turn off, and so effectively what this generates is a feature tree where you can actually group the features like a tree, where if it's 0, it's basically exposes all the other features, and it's like a hierarchy on that. That high level, that's my understanding, but I'd welcome you guys' thoughts. And this is not just another way of actually grouping features. I think it will make more sense when we actually start doing the practical stuff next week. But yeah, I mean, what do you guys think? What do you think, Mayank?
Yep, it's right, because it depends upon the z vector, and it's kind of it's not trained, but the encoder and the decoder, if we think about from a stacked auto encoder perspective, those features are kind of being put on layers. We can, of course, use a graph here as explained in the figure 6. But yeah, the how do I say, the representation here, it's totally how we would expect a particular feature tree, like in a hierarchical perspective, as you have alluded to. So it's just an extension of that in a couple of continuous and how do I say, those branches in a graph type network. So yeah.
So in AlexNet, they used this local response normalization, right? And this is kind of similar or the same. And there it was like inspired by human brain as it operates. And so I'm just wondering if this analogy is valid. And yeah, if you
AlexNet came out like, what is it, like 10 years ago. So I'm surprised they would have anything more than a very basic CNN.
So contrary, basically before we started like working with very big, deep nets, people tried kind of more tricky things, right? And so this local response normalization was one of the, so the idea is to, if we have like, if one neuron is activated, we don't want neighboring neurons to be activated.
Mm-hmm.
And that's how human brains work. And this is kind of similar to what we're talking about right now, right? And but I think that with scale, so maybe because of computational constraints, or maybe because it didn't like yield so much of benefit, it didn't survive to ResNets and are the like more modern CNNs. But first, here I'm not really about vision stuff. So maybe someone working with vision and can give us more perspective on that. And yeah, and maybe this when we get like better computational infrastructure. So basically, what we have now is somewhat limited by what kind of computation is available, right? So we want to big matrix multiplication because that's easily done by GPU, and that's kind of directs deep learning research currently. And maybe when we have like more flexible computational infrastructure, this will come back again, I guess.
Yeah, that makes a lot of sense. Anything to add, Mayank or Sujit or Srinivas, before I move on?
Nothing from me.
Okay. So I'm not a, I haven't been working on images, so forgive me for being a little bit unfamiliar on this territory. I'm back on more familiar territory when we start talking about reinforcement learning and autonomous control. So this is to me a lot of fun stuff. So in this section, I think Jan basically started talking about the world model and in the context of self-supervised learning, I think what he was trying to basically say was there's the direct experience of the world, but the things driving the world are latent spaces, latent features. So we can think of it like self-supervised learning, and we naturally build a model of the world, of the latent space, or the rules behind it. So I think that's how it actually gels into self-supervised learning. So what we have here is, I think he's calling it a world model. So when he's talking about a autonomous intelligence system, he's basically, this is kind of like reinforcement learning, the basics. And I think the TWIML team here is actually running a session on reinforcement learning, which is on Sundays. And if you guys are interested, that is probably going to be a lot of fun, because to me, reinforcement learning is an area of a lot of interest. Anyway, so if you look at the reinforcement learning view of the world, it's typically, your perception of the world, which is the state. There is a framework or model of how the world operates. That's it's referred to as model. It is a different context to say a model in a machine learning. A model of reinforcement learning is really the rules of the world. So I think in chess, it's rules of chess, right? It's not what you do in chess. It's kind of like how, what you can do, pieces go forward, sideways, whatever. And then you have obviously your actions, which is performed by the actor, which impact the world, and the world being the state. And then there's a loop back here. You don't get all the information of the world. You get a fraction of it. When we don't see everything. We just see what's in front of us. So there's the perception of the world. So this is at a very simple level reinforcement learning. And what he's done is added a couple of things, which is what's called a critic and actor, and which is a bit of an advanced concepts in reinforcement learning. And so this helps generate what's referred to as a policy. A policy is what your model is, what you're actually doing. Think of it as the small m model in machine learning. It's basically how you behave. When you play chess, your policy is how well you're playing. As a grandmaster with 1600 or something, score, your policy is going to be very different to someone who's just learning. So the policy is what you do, what are the rules in your mind in order to influence that state. So this is basically a loop. It's a state action, decision sequence. So when you play chess, you have an initial move. your opponent moves, you make a move. So it's a sequential decision making. So it's a feedback loop for once you take an action, it impacts the environment, you're in a new state, layout of the board. That then turns around your perception of the board, which for chess is pretty straightforward, but for some other things, you may not see everything. And then, you act, and then there's a loop. Now, if you unroll that, then we're kind of back to a couple of things that we saw earlier. So what we have essentially is a sequence. So we have a state, and let me kind of go into nomenclature here, but we have a state at time t equals 1. You perform a bunch of actions based on that state, and you have state t. Then you have a next time step, which is t plus 1, t plus 2, and you have actions which go into that. So let me kind of go into, I'm trying to remember what the actual G and P stand for. Obviously, C is the cost within that state. Does anybody recall what G was in his video? In theory, that should be the perception of the actual state action. It's the Q function, I'm assuming. Does anybody recall what G stands for?
So this is a model of the world. It takes a state and an action and returns the next state, right?
Okay. I'm assuming it's analogous to Q function or something, but okay. So when I look at this and I look at him getting very excited about saying that this is not reinforcement learning, I could not disagree more. Hey, I mean, he's Jan LeCun, but to me, this is just standard off policy reinforcement learning with experience replay. I know some of this stuff doesn't mean anything to you, but to me, this is reinforcement learning. And what we're really doing is identifying policy gradients, which is the rules that you're trying to figure out, what the actions sequences you're trying to figure out. So to me, I don't see the difference with reinforcement learning, but I know Jan was very adamant that there is. I mean, I'd welcome your feedback, guys. What do you think?
I think one of the things he was saying, and I had the same feeling as you when I was watching, but I think one point he makes is that the reward function or loss function in the real world, which he calls reinforcement learning, is non-differentiable, and therefore, and which is somehow, kind of doesn't make sense to me, because in that case, I mean, it is reinforcement learning, not implementable reinforcement learning, right? At least with deep learning. But again, I mean, he's Jan LeCun, so yeah.
Yeah, I mean, hey, who am I to question it? But it doesn't make sense.
Isn't the key difference that he makes that related to what you said, Sujit, not just the non-differentiable, but the fact that in reinforcement learning, you actually run simulations to get to where you want to go. Whereas in this, you do not. And that's a very key difference as to why he insists this is not reinforcement learning, because every example of reinforcement learning that I've seen does entail doing things speculatively, figuring out as you go along. And that's not what happens here. So that's a very key difference between. So while there is a similarity in the concepts, he clearly distinguishes it, because in every instance of reinforcement learning, and that I have seen as well, you have to have a simulation, as in you don't know a priori, so you figure it out by allowing the system to go through different parts. And in this case, you do not. Isn't that a key difference that he highlights?
Yeah. My issue with that is that imagine you have a robot, it doesn't, just starting reinforcement learning, you drop it in a room. Whether you use what Jan suggested or use traditional reinforcement learning, the fundamental problem you have is you don't know what to do. How can you differentiate if you don't know what to do? So you must have some sort of a model of the environment. So I think what Jan is basically saying, if I had a model, then I know what the rewards are and it's differentiable. But the big problem with reinforcement learning a lot of the time is you don't know the rewards. And I think Jan's assumption is you do. And how do you know it? Because you have a model of the environment, and that's the way you do it. But if you do have a model of the environment, then you just run an experience replay, actor critic method. So to me, it's the same thing. If you don't know what to do, if you don't know how the environment operates, you just launch trajectories and you explore the environment until you have an idea of the model of the environment, and you have a model-based approach. I think what he's assuming is a model-based approach. But if you have nothing, how do you use Jan's approach? To me, they dovetail together, but I don't know.
So from my understanding, what he was saying is rather like this is not necessarily reinforcement learning. We could view this kind of, so reinforcement learning would be a particular kind of this stuff, right? So that's like, if you want to hold the trajectory, you can learn a controller, which would, by reinforcement learning, which would follow the trajectory you want to follow, right? But you also can like compute a PID controller, which would, given the model of your system, which would follow this trajectory, right? And you don't need reinforcement learning for that. So in this case, it's kind of more general framework, which can in some case, so you can kind of learn a controller in reinforcement learning fashion, or you can apply any other approach, and you can express the problem in this way for different applications. So that's what I think.
Yeah, I'm starting to see it, but I'm still not convinced. But hey, that's Jan. With that, in classical optimal control, there is no actor policy, but obviously in reinforcement learning, there's various, actor critic, on and off policy approaches. I'm not sure if the terms actor critic mean anything to you guys, or on and off policy. If they don't, just let us know. But if you're interested, there is a reinforcement learning thing run by TWIML on Sundays. But anyway, there's no actor policy module. His assumption is basically you just run trajectories. The robot runs into the wall until it figures out how not to run into the walls. And essentially what you're doing is identifying an action variable for a state, right? And there's a long history of optimal control, and I think he's referring to one of the earlier ones, which is model predictive control. Yeah, this is from the 60s. Okay, so I think this goes back to what you were saying, Arta, which is that we don't want to go through the complicated process of back propagating every time we want to make a plan. So to address this, they do the same thing we did for variational autoencoder to improve the sparse coding. We train the encoder to directly predict the optimal action sequence from the world representations. Okay, that to me is Q actor critic, but hey, but okay, that's fine. So in this regime, the encoder is called a policy network. Yeah. So what we're doing, and by the way, the pi means policy. So we have a state impacts the function. We basically sample the environment, which is Z. The policy dictates the action, and that's an input. So you have input into what you're trying to predict being the state, there's a latent unknown variable which is impacting the environment, the action, and going to new state, that dictates a cost. The cost is essentially a proxy for reward. So you can treat it like that. So essentially this becomes very similar to a variational autoencoder. So once we train this, one thing that I struggle with is this, that you can unroll this, but in theory, this can be infinite. The trajectory can be very long. And there's no concept of kind of like a, so for example, if you get stuck in a loop, if you have a trajectory, you need to have some sort of a attenuation of the rewards or the cost function as it goes on. I mean, what's your take, Arthur, on that? Because in theory, the trajectory can go on forever. So you need to have some sort of a attenuation of the cost as you go down the path for the maths to work. Because the current... I'm sorry, I guess what I'm trying to say, I'm looking for the words, but in reinforcement learning, there's a concept of the current reward is basically the sum of the value of the current state is equal to the reward you're going to get, plus the discounted, that's what I was looking for, discounted rewards over time. One difference here is that the cost, which is effectively the reward, is not discounted over time, it's static. Mm-hmm. So we in reinforcement learning, we discount the reward over time because the present value of a reward is the immediate reward is worth far more than reward 50 steps down the line. We're not really doing that here. We're just basically saying the rewards all the way down the trajectories are all the same. Mm-hmm. Just wondering what that's a key difference, I think, as well. Don't know if you got what you guys thoughts about that.
Mm-hmm. Yeah, because in PPO type of methods, we have some kind of approximation that is being applied to the selection of the best state action pairs, depending upon the policy network. So that's not also being done here. So coupled with that, as he has alluded to, I think so in his video with the figures that he made and the explanation that he gave. So yeah, there were 3 to 4 factors, I thought, which combined together to form why this world model is not using the reinforcement learning aspect of it, as opposed to the autoencoder stuff that he mentions.
Okay. Yeah, I think that's the big key difference. You're absolutely right. So I think we've kind of touched on this, which is, the main differences between RL and what we've studied up to this point. In reinforcement learning, the cost function is a black box. I'm not sure if I'd agree with that, given that there's a lot of policy gradient methods out there, but okay. I think on policy methods would try and understand that, but I know where he's coming from. But this is definitely true. We don't use a forward model of the world to step through the environment. We interact with the real world and learn the result. To some extent, that's true, but you also have experience replays and also off-policy learning methods. So I think to some extent that may be mitigated. Yeah. So this goes back to a couple of other things, which is reinforcement learning. The cost function is not differentiable. Yeah, I think that makes sense to some extent. I think discounting causes some issues, but I think you could argue that the other way. And then the other issue is, how do you explore the space efficiently? That is probably true. I think the key difference for me, and I can't get over it, is essentially the only way Jan's approach works is if you have a model of the environment, a perfect model of the environment. In that case, absolutely fine. If you want to play chess, you know the rules of chess, you can map it, you can use autoencoders. But any other environment where you don't have a model of the environment, then I think that you kind of have to go through the exploitation paradigm. Yeah. So, sorry.
Yep, I agree.
So I think we've kind of covered the reinforcement learning, and I think we've discussed the pros and cons. I think I know where, my take of where he's coming from is this, which is reinforcement learning problems, essentially self-supervised problems. You're trying to identify the model or the latent space that's driving the model of the environment, which drive your actions. So I can see the synergy there very much so. In the time we have left, I'm not sure how much time we have. Do we have time to go quickly through GANs?
Yep. Yeah, I think we have half an hour more. Yeah.
Oh, we do. Oh, okay. Sorry. In that case, is there anything that you guys aren't familiar with reinforcement learning or stuff that we should actually go through in this space? Sujit, Dato, Srinivas, I think Mayank is probably fine. Sounds like he knows a lot in this space. Okay. Okay, great. So I think we've in this series touched on GANs before, and I think the presenters actually talk about a couple of analogies around this space. So, I can see where they're coming from when they talk about like GAN being an energy-based model using constructive methods. Are you guys clear on how GANs work or how they're put together? Is this something we should talk about? The analogy I think that was used about the bank robber and counterfeiter and all that stuff in Italy. I'm not sure if that makes sense. Does the concept of a generator and a discriminator make sense? Or should we kind of like go through the analogy? Should we quickly go through it just to give you an idea of what it means?
Yeah, sure.
Okay, so the analogy I would use, or what I say to people about GANs is this, similar to I think what was said on the video is, imagine you have a bank teller working in a bank, and people come to the bank and they want to change money, and person walks in. You don't know if that person walks in the bank is a counterfeiter or just a member of the public who just wants to change their money. They approach the teller, hand over the money. The teller's job, the discriminator, is basically to turn around, look at the money and say, is it legit or is it not legit? So as that teller in the bank sees more and more counterfeit notes, it gets, he or she gets better at identifying counterfeits. But that teller doesn't really know if they're going to get a real or a counterfeit note. But the trick here is that the teller is a really nice person. They provide feedback to whoever comes to them. If they give them a legitimate, currency, they go, thank you, here's your change, whatever. If it's something that's a counterfeit, provides feedback and says, the note is too big, reduce it by this much size, or the font on the note, or the paper's wrong. It provides feedback and sends the counterfeiter back on its way. So over time, over millions of iterations, what tends to happen is two things. The discriminator gets more familiar with identifying counterfeits, which is great. But more importantly, the counterfeiter, because of the feedback, gets better at generating fake notes. It's been given feedback that the note should be smaller, should be this type of paper, the font should be changed, the face should be moved a little bit. Eventually, with all this feedback, it will produce exactly the same, the counterfeit notes, which are completely indistinguishable to the real notes. So in that case, at that point, the teller becomes useless because the counterfeits are so good, the teller cannot distinguish between them. So in the analogy, what you have is a generator, the counterfeiter, who through feedback learns how to generate fake currency, or in this, fake data. And then the discriminator, who's basically learns to identify it. But when it's all done, the discriminator is useless. You can just throw it away because it cannot identify the differences because the counterfeits are so good. At that point, the counterfeiter, the generator, will generate exactly the same data in exactly the same shape, the feature space, as real data. So at that point, you can start, the generator can generate fake data or synthetic data, but that is within the shape or within the feature space of the real data. So what I think they're really saying here with the energy function is this. Initially, the generator, the counterfeiter, will land far away from, and I always get these two mixed up with high energy or low energy, but it will land far from, I think, low energy space. And then through feedback, it will be forced into the low energy space. And at that point, you're essentially, it's feeling its way through feedback to identify the low energy space through millions of cycles. So that is a very, simplify. That's how I rationalize it in my head. I'm not sure if that helps, or but that's the way, my understanding. I mean, Arto, Sujit, Srinivas, Mayank, what do you think? I mean, does it make sense, or did I confuse you even more?
Yeah, it makes sense. I actually liked his energy-based thing as well. I mean, pushing down on the data versus, pushing down and pushing up everywhere else, and you slowly move the energy contours back to where it should be. Right? So, yeah. But good analogy. Thank you.
Yeah, I'm I've heard a concept of energy functions. I'm not sure. I'd welcome your feedback. I am not a convert. To me, it is just the terminology issue. I don't see any aspects that or where it's actually been implemented. It's a useful concept, but I don't know if you guys have seen that implemented in any sort of meaningful way, or is it just a concept?
I think it's a concept, and in the sense that everything is an energy model, and everything is a special case of an energy model, right? So that's how Jan LeCun kind of approaches the whole thing. It's his idea, I guess. So it's like the overarching concept in his head, and everything actually are special cases. So and he explains why. So so in that sense, yeah.
Yeah, I had a similar question that I wanted to hold till the end of the section, because we've been through three, and so I totally agree that it's a reconceptualization of all of the problems and an overarching kind of concept of energy. But my question is, has that enabled, I mean, the reconceptualization is useful sometimes if it opens up avenues or solutions that didn't exist prior to the reconceptualization, right? I mean, if you can think of a problem in a new way and therefore solve things that you couldn't before, then it's immensely useful. Are we at that stage with energy-based, or is it just a reconceptualization? Are there problems that are being solved because of the reconceptualization that haven't been solved otherwise?
Yeah, I don't know. Good point.
Yeah, the concept of energy function comes from physics or engineering, signal theory, really. And it's a useful concept. I just don't see the ethic reconceptualization is really helping. My other problem with it is that he's really saying it's done at inference time, not at training time. And that completely just goes over my head. So my day job is actually looking after inference systems, right? So most of you guys are data scientists, you train a model, great, you throw it over the wall to your MLOps people, you put it into production. Everything we've been speaking about was training, most of what we've been talking about. But he's saying it's at inference time. When it's in production, that to me is like a miss.
Yeah, there though, he gives, if you go back maybe a couple of slides back on the note, there is an aside, and I found that aside, and he kind of talks to it. I forget whether it's in this lecture or in a previous lecture, but conceptually, conceptually that helps clarify it, because what he's saying is, if you do something per sample and you are doing per sample, then he calls that inference. Whereas if you're learning something, then you're learning with respect to the parameters. Whereas the Z values, he calls that inference, even though you apply stochastic gradient descent, which is the same optimization technique, but you're doing it per sample, therefore inference, whereas parameters are done for the entire data set, therefore learning.
So is it a terminology thing? So traditionally, in the industry, the concept of inference means you've taken a model, it's done, it's trained, you put it into production, now you want to get predictions out of it. Is it a terminology issue then?
It is in, and that clarification of why he insists something is inference and not learning versus what he defines as learning is learning across the data set, and applied to the latent variables, he calls stochastic gradient descent or whatever to find lower energy points, which you do with respect to the latent variables. He calls that inference because it's done per sample. That's at least his definition of when he calls something inference versus when he calls something learning. And learning is something that happens over the parameters because it's across the data set.
Okay.
Well, for my understanding, although we optimize over Z, we don't learn anything. We just try to, this is inference, what he calls, when we optimize over Z. So correct. The latent variable.
Yes.
And we just find a value which value of Z, which will correspond to low energy space, right? Correct. But we don't learn anything in the process. We just are looking for this. So gradient descent is not only for learning, right? It's just an optimization technique, and we are trying to find this good value of Z to be able to sample from the energy function. So yeah. So first we optimize or marginalize over Z, and then we can apply this for inference, right?
That makes a lot of sense. So he doesn't mean traditional industry inference. He means you've learned the Z, the space or the feature set, and you're essentially optimizing over Z.
Also, Mayank has cited a particular thing where the reconceptualization as an energy-based model actually helps.
Yep, it's with respect to Sentry. It's a selective entropy optimization for an unsupervised domain. So what they do here is they kind of, with respect to the initialization, they optimize, they first try the conventional approach and then the entropy optimization with respect to the consistency of a particular uh, 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 class of variables that, or a class of labels here, which they are trying to predict. And then with respect to the argumentations and other stuff, they try to address the data and the label of the distribution shift and the drift that occurs. So in an online settings, with when you have a continuous stream of data that you have to deal with, this kind of conceptualization helps in trying to uh, uh, think from a different perspective to reach a solution, such that in a industrial settings, those problems won't be those problems can be solved. So yeah, simply.
Okay, thank you. That makes sense. Thank you, guys. So just to kind of like go back to GANs. So one thing I wanted to mention about GAN, and I would like your perspective. Most data scientists I speak to basically treat GANs as toys. And I think some of that stuff is covered in the next lecture. There are a lot of negatives to GANs, and I think that's covered in the next week's discussion. Have you guys seen GANs out in the industry used extensively or very much? I mean, I've seen variational autoencoders quite a bit, but not GANs. And I'm just wondering, is my perception that it's more of a toy than anything else correct, or is it used really extensively?
Yeah, I have a colleague who's kind of an expert on it, but he doesn't like them because, they're very hard to train. So
what does he use instead?
Most of the time he's doing, like he said, autoencoding, autoencoders or other. He tries to stay, like he did his PhD on GANs, but then he tries to stay away from,
Use the pain.
Yeah.
Okay. Okay. Just to quickly go through what we kind of like touched on earlier. A basic GAN consists of two parts, which is a generator, which is the thing that's trying to identify the low energy parts of the Z space. And it produces samples intelligently. And then you have a discriminator, which is in the analogy I have, or the robber, I think, in the analogy from the lecture. I've never heard it called a critic, but okay. Which essentially is a cost function that I guess is the energy model, and what they're doing is they're adversarial because they're both trying to be optimized, and they're optimized together. And I think next week we're going to drill down into more details of that. So I think they mentioned that there's two inputs to the GANs, which are the training samples and the contrastive samples. In this case, the training samples essentially, I think if you go back to the analogy, is the real currency that the teller sees, and the contrastive samples are the generated, in the analogy would be like the fake currency, the counterfeit. And so the GANs passes these samples through the discriminator, and it's random. And I've heard of examples where GAN has been trained where you alternate between the two, and the GAN just basically picks up that every second one is legit. So you have to be careful. It has to be randomly go through a GAN. And then it makes the energy go down, i.e. you identify where the generator, that its sample space is exactly the same as the training samples. So GAN's samples use latent variables from some distribution. So, if we're talking about like, currency, it's whatever the features of that currency are. But there are latent variables, and then the generator is trying to identify that feature space so that actually, you can think of it as an energy function, so that once it arrives and understands the shape of that space, it then essentially is able, the discriminator is not able to actually identify the differences, and you arrived at a low energy, I think in yarn speak. So the loss function for the discriminator is made up of the real and I think the fake, essentially, the training sample and the contrastive samples. This is my understanding. Is that correct? I think we go into more detail next week, but that's the way I read this.
Yeah, pretty much. I mean, I think, so for once the generator is trained, I mean, you can feed it random noise and it learns the space well enough so that it can actually generate believable samples. So Yuri actually mentioned here that he's using, or he has seen them used for physics-based simulations, which actually seems quite cool, right? So, yeah.
Yeah, no, I've heard of it being used for physics, and that is actually mind-blowing, which is instead of trying to do the traditional physics thing, which is trying to identify how things work and then figuring out experiments to basically validate that. It's basically using real-time data to identify patterns and work at backwards. So trying to figure out how the universe works from the data, which is mind blowing. Whether the latent spaces identified can then be turned into mathematical concepts is a different thing, I guess. That's mind blowing stuff, right? For me anyway.
So I actually didn't mean like so much a model of physics, but I've seen them successfully used in the cases where it takes a lot of effort to actually create simulation of the real world, and GANs can do it much quicker. So if you want to like do some sort of scene generation for your bigger system, then GAN is an interesting technique to try.
Oh, so you're just creating synthetic data? Okay.
Yeah.
Okay.
And the other use that I found really interesting was basically to kind of use GANs for segmentation classification problem. I've seen this recently, where basically you just you learn how to draw your kind of maps, segmentation maps. I may try to show example next time.
Okay, no, that's interesting. Okay, so I think we've got 8 minutes, but really just quickly to finish off. Obviously, this is the loss function for the discriminator, which is based on the training and the contrastive samples. Now, for the generator, the loss function is based on going to work through the maths. G is the generator of the neural net that which generates the fake data. So you want the loss function of the data that's actually the contrastive examples to equal the training set loss. That's my understanding, which makes sense. Let me know if I'm reading it incorrectly. There's a deep dive into this next week, so I kind of don't want to read through this, but there's a good overview, I think, with Alf next week. Sorry, it's in the video, but I'll cover that next week, if that's okay. Any other questions on GANs or reinforcement learning or autoencoders?
So just a quick question, somewhat unrelated to what we talked about. So I was listening to this interview with Christian Szegedy, and he mentioned that like he believes that stacked autoencoders would be like one of the next important things in deep learning. So I was just looking for some, papers, research that show any like important results, but I didn't find them. And I'm wondering if anyone knows what was he referring to, so what kind of projects.
I'm not an expert in this space. I mean, I defer Mayank. Anybody else? Any experience with stacked autoencoders?
I know some basic stuff, but what was your query again, Arto?
Yeah, excuse me.
What was your query again?
Yeah, so I was referring to this interview with Christian Szegedy, who like mentioned that he believes that stacked autoencoders will be one of the important things in the nearest future, and I'm wondering what research does he refer to, or if anyone knows. Yeah, so what's this all about?
No, I'm not particularly familiar with that work. If anybody else has.
No, I'll ask around work and research department and try and get you an answer for next week. Well, I'll add it to the stack.
Okay, great, thanks.
Yeah, I'm not an expert in this space, but we have a research department that does a lot of that stuff. Cool. So thank you for listening to me. I know I'm definitely not an expert. I've learned more today than I think you've learned from me, but thank you for your patience. Have a wonderful weekend, what's left of it.
Thanks, Joseph. Thanks a lot.
Thanks, guys. Okay, bye.
Thank you. Thank you.